First floppy disk system made for a personal computer is the one you see here, made by MITS for their Altair 8800 computer. It came out in early 1976. And like most of the first generation of floppy disk systems for these early personal computers, it used a hard sector controller inside the actual computer. And that's because making a soft sector controller at this point in history was far more complex. For example, you may recall seeing this drive cabinet in a number of my other videos. It's a dual 8-inch drive cabinet with a built-in soft sector controller. It implements the IBM 3740 8-inch soft sector standard. Now what you're looking at here is actually just half of the controller. There's another board directly below that, same size, same number of chips, same complexity, about 130, 140 chips in total. And that complexity wasn't enough logic to actually even format a disk. So it gives you an idea how complex it was to make a soft sector controller at this point in time. Of course, all that would change over the next year or so with the introduction of the 1771 from Western Digital. This was a 40-pin IC that was basically a soft sector controller on a chip. And by the time it was in full production, about a year from now, it was actually cheaper and, of course, a lot simpler to make a soft sector controller than even a hard sector controller. And, of course, that's the way the industry went, and the hard sector controller soon went the way of the dinosaur. All right, so back to this Altair system. It's a hard sector controller, but it's really not that simple in the end, which I often found intriguing because everything MITS did was just as bare bones and cheap as possible. And yet all this added complexity of this floppy disk system didn't buy them anything. It didn't make it faster or more capacity or more features. It just made it more expensive, harder to build, and less reliable. So I thought it'd be an interesting project to see if I could make my own disk system for the early Altair using only parts that were available back when MITS designed this floppy disk system, with the design goal, of course, of making it simpler, easier to manufacture, more reliable, and less expensive. So that's what this video is going to be about today. To get started, let's go ahead and take a look at how the original Altair floppy disk system went together. We're going to start over here on the computer to begin with. Here you see the disk controller that was inside the Altair computer itself. It's a two-board set. You have about 20 wires that go between the two boards for communication. And then some of the signals to the disk drive come from the first board, others come from the second board. All that wiring is through these multicolor conductors you see here. They're all hand-cut, stripped, soldered, one pin at a time. Those then eventually make their way into this jacketed, twisted pair cable that you see here, and terminate into a DB37 that is typically installed in the rear panel. However, in this early 8800 that I have, there are no DB37 size slots in the back. So there, this cable would just be hanging out the rear of the cabinet. All right, then to hook up the first drive in the system, you would make another cable out of this same multi-conductor twisted pair wiring that would run from the computer over to the first drive in your system. And here it would come in through a DB37 on the rear and go straight to this board you see here. This large board is called the buffer board. Its job is to repeat all the signals to and from the next drive in the chain. So it comes into the buffer board through this cable from the computer, goes out through this cable, which is another DB37, you can see it down there. And then you would hook up the second drive in the chain using the exact same cabling as came to this first drive. And you could hook a third or fourth drive if you needed. Although, of course, 2 drives is the most cost-effective and useful combination typically. All right, the buffer board also has a ribbon cable that talks to the drive mechanism itself. This is a Pertec FD400, and this is how the relationship between MITS and Pertec began, was by MITS choosing this drive. They chose this drive because it was less expensive than competitors like Shugart was at this point. The downside of this drive is that it can't be multiplexed. That means you can't have multiple drives on a single ribbon cable. So the first thing you have to do when you go with this drive is have dedicated electronics per drive. So by saving money with this drive, they then turned around and gave up most of that savings by having to build this buffer board for each drive mechanism in a system. So unfortunately, yeah, the savings was kind of short-lived there. Now this particular drive never sold to the general public as you see it here. It's using standard ribbon cables with push-on IDC connectors. In reality, for the 2 years this drive mechanism was sold, it used the exact same hand wiring that you see over here in the computer. In the end, by the time you did the hand wiring in the computer, the wiring between drives, and built a typical 2-drive system, you had a total of 688 wires that had to be cut, stripped, and soldered to wire up just the data cables in that system. So that does not include any of this power supply wiring. It does not include soldering all the components on all these circuit boards. It's just this wiring here, 688 connections. And as you can imagine, that would take even an experienced technician a couple of hours, and there's bound to be a mistake or two on almost every system that has to be found and fixed. So that was just a manufacturing nightmare, and further added to the cost of this system versus something like the cabling you're accustomed to, where you just push on a connector for each drive and you're done with simple IDC connections. Now, in the end, Pertec decided not to go this route. Instead, they put those buffer boards and 2 drives into a single cabinet, not the top one that I showed you earlier, but this one below. So this is 2 of the Pertec drives with 2 buffer boards that use IDC connectors, very similar to the one you saw on that computer, but not identical. And they did that and canceled the product line where you had just 1 drive per enclosure. And that's because the most useful and at least for small business and serious use configuration was a 2-drive system. If you'd like to learn more about the problems that MITS and Pertec had with this drive cabinet, as well as the move to this 3202 dual drive cabinet that I mentioned earlier, take a look in the description of this video and you'll see a link to a video there that goes into more detail, especially about this 3202 dual drive cabinet. I'd like to also now throw up a picture of what this cabinet looks like, the normal drive cabinet looks like, using the hand-wired multi-conductor twisted pair ribbon cable that we showed you earlier. And this is how it was actually put together for the 2 years it was in production. Now that we've looked at the design of the original Altair floppy disk system, let's take a look at the design that I came up with. Instead of using the Pertec drive mechanism, I'm going to use the Shugart 800 series drives that you see here. At this point in history, Shugart was quickly making a name for itself. It had good success in the mainframe and many computer marketplaces, and of course soon it would come to dominate the microcomputer market for a number of years to come, especially with their introduction of the 5¼ inch drive. Now these drives were built like a tank. It's not hard to get one of these 800 series drives you see here up and running reliably again, here almost 50 years later. And the restoration work is generally fairly minor, just some cleaning and lubrication to get everything moving again. There's a good chance it's working reliably for you. Pretty impressive for a electromechanical device like this. Now the frame on this, if you look at it, is a die-cast aluminum frame. It's very rigid. And this was important in this time in history because alignment of the head to the media was maintained mechanically. And by alignment, I mean position of the head over the tracks on the diskette. That would be your radial alignment. Alignment of the head angle to a radius on the disk, that's your azimuth. And then the position of the data on the disk relative to a sector or index hole, that's your index alignment. And because this drive is rigid, once those alignments are established, it tended to keep its alignment. Now MITS, on the other hand, with the Pertec FD400 drive, had a real problem with their systems losing alignment. Here we take a look at this FD400 drive. You can see that it's made out of sheet metal instead of a cast aluminum frame. And this was a technique to try to save money. So once again, by saving some money, MITS ended up costing themselves money because of the problems this drive had losing alignment. For example, just picking up the drive cabinet that the Altair was in transferred enough torque to this drive that it would lose alignment quite often. Your own disk suddenly wouldn't work anymore. So to get around this problem, they tried a few things. Let me show you. Here is a drive. This is actually an FD500, but they did the same thing on the 400. They added this stabilizer bar across here in order to improve some of the rigidity. And then they also went to at least MITS did in the drive cabinet, recommended a 3-point mounting. So you'd mount here, here, and then here. And then the third corner was left up in the air about 1/4 inch so that when you picked up the drive cabinet, it didn't transfer all of the torque, at least, to this drive. In addition, to help improve index alignment, they changed the write timing on the floppy controller itself to better center the data between the two holes of two consecutive sectors. That way you've maximized the amount of space at the end and the start of the sector to allow for differences in index alignment. But despite all those improvements, it was still generally an issue that it was not hard to lose alignment on these discs. And again, so by saving a bit of money going with this Pertec drive, they ended up costing themselves money with unreliability and the fallout of everything from warranty repair to disgruntled customers. The data cabling for these drives is very simple. In fact, it's probably what you're more accustomed to than what we saw inside the Altair cabinet. Basically, to wire up a typical 2-drive system like you see here, you just pull a 50-pin ribbon cable to the length you need, push on a connector on one end for each of the 2 drives, and then on the other end of the cable you have a connection that goes into your disk controller, and that's it. Literally 60 seconds of work and you've done all the data cabling. Simple, reliable, very inexpensive to do. This compares directly. This is equivalent to all the wiring we saw in those Altair cabinets. For example, like we talked about, a 2-drive system would be 688 connections that had to be cut, stripped, and soldered one by one to do the same thing you hear with this single ribbon cable. So you can imagine the cost savings in terms of manufacturing, and then the reliability improvement right off the bat, off the manufacturing floor, plus in the field. All that was a big cost saver for all this. In addition, this simple wiring made it very inexpensive to make the cabinetry or the enclosures for these drives. For example, if we look over here, we can see a typical 2-drive system with the Shugarts. This is just a very generic sheet metal cabinet. Nothing special about it at all. So that's inexpensive. And inside, it doesn't take much of anything. So for example, here we see we have space for the 2 drives up front. And then in the back, we've got a single power supply that takes care of both drives. We have a single cooling and power entry that takes care of both drives. Again, no other electronics, no buffer boards or wiring, just this ribbon cable, just like the one we showed you, that hooks from one drive to the other and then runs over to your computer. And that's it. So again, simple, inexpensive compared to doing a 2-drive system with the way we saw the Altair put together. So there's another cost savings for the typical system that would be built and shipped. Here you can see the floppy disk controller that I came up with to use with my version of the floppy disk system. As you can see, it's down to a single board instead of a 2-board set, and it's a very simple board at that, just 12 ICs as opposed to the 59 ICs that comprise the 2-board set from MITS. Now on this board I do have a single LSI chip. That's the 6852 made by Motorola. This is essentially the synchronous version of the 6850 UART that was on the Altair 882SIO serial board, for example. I use this chip to serialize and deserialize data to and from the surface of the disk, and I also use it to establish sync with the data on the disk. It uses a 16-bit sequence to establish sync, as opposed to the 1-bit sequence that's used in the Altair controller. So that's a more robust and reliable mechanism as well. All right, and so with this simple controller and this simple cabling and these Shugart drives, I can duplicate all the capabilities and performance of the original Altair floppy disk system. And one obvious question is, well, if it can do everything that system did, how can this be so much simpler? When it comes to data cabling, well, I think that part's pretty obvious, so I'm not going to dig into that any further. But what's not so obvious would be, why is this controller so much simpler than the 2-board set from MITS if it can do everything that the original MITS controller could do? And there's more than one reason or more than one answer to that question. However, one of the main reasons was actually a common problem at this turning point in history. That turning point being the introduction of the microcontroller. In the end, the 2-board set from Motorola, the 2-board set designed by MITS was designed completely independent of the software. And the net result of that is that there was numerous functions implemented on that board in hardware that could have been done for free in software with no hardware performance penalty and no software performance penalty. So for example, there are 14 one-shot timers on the MITS controller that either directly or indirectly set and clear status bits that software has to monitor in order to decide what the drive is doing and what to do next. And in all cases, these bits are monitored in software using very tight little loops, just 3 or 4 instructions long with interrupts disabled while they're looping. Obviously, that means software can do nothing else, so it might as well do the timing and do any of the logic that might be associated or tied in those timers together. So by the time you do that, you've freed up a bunch of chips and get yourself down to just a single board. In addition, there's other logic, not just the timers, that I did the same thing with. And once you've gotten down to one board, you realize, well, I can eliminate the chips that were used to buffer and receive signals between the two boards. That frees up some more space. And then you realize, well, I can also get rid of the connector space and the wiring space for the wires that went between the two boards. That frees up more space. And in the end, you're left with what we see here, a very nice, simple solution. Before we move on to the demonstrations of the new floppy disk system, let's go ahead and talk briefly about the specifications of the original Altair system that the new one had to meet. This is an 8-inch drive with a formatted capacity of 308 kilobytes. Notice that this is quite a bit more than the 250 kilobytes of the IBM standard, the soft sector standard for 8-inch drives. And this was one advantage that the hard sector drives had over the soft sector drives, at least with these 8-inch ones, is you got about 23% more capacity out of it. Now in my version, I'm actually able to get 365 formatted kilobytes out of it. So that's another 18% more than the Altair format even. And in addition, I was also able to increase the amount of free space before and after index holes so that it had less issue with index alignment. Increase the amount of space by about 2.5 times. So this extra slop, along with the fact that the drives are so much more rigid, means that you'll really never have an issue with these drives losing alignment during any sort of normal operation. Now in terms of performance, the original Altair system could actually keep up with the full transfer rate of the 8-inch drives. So theoretically, if you wanted, you could read all 32 sectors in just one revolution, just one right after the other. Same with writing, you could do those all right in a row as well. Unfortunately, no early Altair software took advantage of this capacity or capability at all. For example, Altair Disk Basic only read 2 sectors per revolution. I mean, it took 16 revolutions in order to get all the data off of a track. And then later on, when Lifeboat came out with CPM for the Altair hardware, it read about 4 sectors per revolution. So it still took 8 revolutions just to get all the data off of a track. So even though the software didn't need this full speed capability, since the original Altair controller could do it, I made sure my controller could do consecutive sectors full speed as well. Now, as part of my demo, I'm going to go ahead and show a version of CPM I created that actually takes advantage of this full transfer rate, so we can see the performance improvement that doing that might have given people back in the day. Now again, this is not unique to my controller. The original controller could have done it as well, just nobody wrote software to take advantage of that in the day. Now I do have a version of CPM out there for a number of years that does take advantage of the full speed of the original Altair controller, and if you want to try that on your computer, I've put a link to it in the video description. All right, let's move on to some demos. To demonstrate the new disk controller, I'm going to use this early Altair 8800 computer. Inside, we've got the new disk controller here as the first board. Behind that is an 882SIO that we'll use for our console interface. Behind that is an original 8080 CPU board for the Altair. And then finally, I've got a combo EEPROM and RAM card to round out this system. We'll connect the disk drives with the 50-pin ribbon cable to this connector on the disk controller. And we're going to use that 2-drive cabinet I showed you earlier. That will be housing our 2 Shugart 800 drives for the new floppy disk system. Now as part of this demo, I'm going to go ahead and fire up an original Altair floppy disk system as well, running original software. Here are the 2 8-inch drives. Now those do have the dark 8800B style faceplate, but internally they're still the same as the one I showed you earlier. And of course the 8800B itself has no performance difference versus the original 8800, just some other enhancements that had nothing to do with performance or memory capacity. So we can compare these two directly. All right, so let's go ahead and get this fired up. We'll have these two consoles right next to each other so we can see how they behave side by side. All right, let's go ahead and get this system booted. I've created a boot ROM that runs at F400 in order to boot this new disk drive. We'll go ahead and turn the computer on, give it a hard reset, choose F400 on the front panel and examine that. That sets the run address, and when I hit run, it'll then boot. Let's go ahead and get this into view here. See if we can get the drives as well, just for this boot process at least. All right, let me go ahead and put the disks in. That's the boot drive, that's the second drive, and I'll hit run. And you see it's up and running already, very quick. CP/M always did boot pretty quick. Let me see if I can get this closer view here. All right, so at this point, there's really nothing amazing or new to show you. It's just CP/M. I can do a directory and we can see what's there, or I can do a sorted directory. This is a program that runs. The dir command is intrinsic, of course. We can see what's over on drive B. I actually have the exact same content on drive B. In fact, I've made 4 identical disks so that we can compare the new system with the old system. And in doing so, I'm not taking advantage of the larger space that I can incorporate on this new drive. Instead, it's duplicating the original Altair disk, so I'm comparing apples to apples, so the exact same disk layouts and everything. We can make sure we have a different file on disk B so we know it truly is different. Let's copy a file here. We'll call it, let's call it diskb.txt, and we'll copy the README file over here to drive B. Well, I messed up something there. Let's see. b:"diskb.txt equals readme.doc. That looks better. I made 2 mistakes in that. All right, so this will create a disk on drive B. That's what we need. All right, I actually want drive B. So we look over here on B, we should now have this diskb.txt. All right, and we can look at what that is. That's on drive B. All right, so at this point, this is just CP/M. We see our new disk system works just like we expected. Pretty much demo over. However, what I'd like to do now is go ahead and boot the second system, which is the original Altair system. Let's go ahead and turn on the computer, turn on these drives. All right, and this boots from F00. So do a reset, F00, hit run. And now we have Lifeboat up and running. So what I'd like to do is do the same thing on each of these computers. Let me see if I can get this into view on both of them, so we get a feel for the difference in speed on these two. So now again, the only real difference here is that one is taking advantage of the fact that either of these controllers could have read straight sectors instead of just reading 2 sectors of revolution or 4. But right now the new controller is doing it. The old controller with the old software is not. But it's truly a software function, not really a function of the controller itself. All right, so if you just did a dir on both machines, and hit return at the same time, don't see much difference. You can see this comes out a little bit quicker. If we do an ls, this has to load a program. See, this loads a little bit quicker and it's out. Now that one's out. Other things with more disk activity, you really notice the difference. For example, if I was to run, there's a program here to run CRCs and calculate CRCs of files. Let's do everything that starts with an S that's a COM file. I'm having a really hard time typing. I'm gonna have to move. There we go. Now let's run both of these at once. Yeah, and you can see over here on the left, we're making good progress already. We're several steps ahead of the computer on the right. It's done already. So you can see the kind of speed advantage we get from this. For example, let's run mbasic and load Star Trek. And 1, 2, 3, go. So MBasic itself is a large program. It takes quite a while. You see here it's up already over here, and now it's loading Star Trek. On the original Lifeboat system, okay, so it's running over here now. Here we've just got Basic running, and we're still waiting on it to load Star Trek now. All right, now it's up and running as well. So you can see the kind of difference in there. In the end, it ends up being about anywhere from 20 to 70% faster, depending on what you're doing. Even just to return back to CPM. 1, 2, 3, go. So we're back already on the left, now on the right. Do something with 2 drives. Let's see, let's do an ASM, this program. The .aab means we take the source from drive A, we put the object file out to drive A, and then put the listing to drive B. So this is going between the 2 drives back and forth. Go ahead and run that, go. Let's see if we can watch the drive go back and forth here. Right now it's mainly on drive 0. Now it's opening up drive 2 in order to write the listing. You'll see it going back and forth between these 2. Let's go ahead and watch it when it finishes. All right, and this one's done already, the one that's taking advantage of using the full speed of the disk. Now it's not 8 times as fast as we might have expected based on what we said earlier. That's because now software, the execution of the CPU, becomes the limiting factor as opposed to the disk. Here we're limited by the disk. Okay, now that's done as well. All right, well that does it for this demonstration. It does it for this video. Again, this little speed up has nothing to do with the controller. That's just the software. Either controller could have run at full speed like this instead. I'm going to set some of these disk drives and machines off because there's a lot of noise. You'll hear it get quieter and quieter as each of these gets turned off. But anyway, so we were able to accomplish our goal. I was able to create a version of the disk system that did everything the original did, just as well or better. But before I pat myself on the back too much, I have to make note that it is much easier to go second. Hindsight is 20/20. It's very easy to look at an existing design, pick it apart, and figure out what you could do better. It's especially easier when I have plenty of time. If you think about it, when the companies like MSI and others went second, they were still in a time crunch. They still had just been exposed to the Altair and a little bit of this at that point in time. Whereas I've got 30, 40 years of exposure to mini computers, microcomputers, and all sorts of things. And I've got all the time in the world. So the amount of experience and exposure I have to draw from is way more than anybody back then would have. So it's not really a fair comparison. You know, MITS is getting dinged for how poor some of their hardware designs were, and they're not the best. But again, they did it first, and they were groundbreakers and trendsetters that got this kicked off and started. Sure, somebody else would have done the same eventually, but they were first. So hats off to MITS for doing this. This was a great project, a lot of fun, learned a lot, and it was exciting to see it all come together.